Well, at some point when we get more students, we should discuss what to do tomorrow and Thursday. Because at the end of last lecture, I was made aware of a technical problem. And the technical problem is that all size students are required to attend the lectures during the PI day or the PI days, right? So that will happen tomorrow and on Thursday in the afternoon.
Do you mean the CFT lectures or the PI day?
PI day lectures.
Yeah, so the technical problem we have is that all of size students are required to attend the lectures during the PI day.
CFT it's 9 a.m. and the PI day is just from 2.
Oh, because you're thinking that you already solved the problem. I see. You're assuming the solution already.
No,
I see. Oh, it was already... Okay, so the only one who didn't know. I see. So I was aware of the problem and the solution yesterday. Now, I see. So
you don't want to come at 9 a.m.
No, that's not the thing. Is that I mean, I have a family, and then there is a little technical problem exactly at 9 a.m. So I can make it at 9:30. So what we can do. So here is a proposal. We do 9:30 to 10:30 tomorrow and on Thursday, right? So, and on Friday, what we do is that we have our regular lecture, have a break, and if we need more time, we continue a little bit longer. How about that? That's one possibility. So, so we should be able to get everything done in the same. No problem. Okay, and then the proposal is that on Friday we have 3:30 to 5 p.m. and then then we have a break. I mean, if needed. Well, if needed, if we need a break. If we don't and then yes. Okay, so that's a proposal.
And so tomorrow morning and Thursday morning here in the same place?
That's a good question. Do we know? It's delocalized at the moment.
I think I'll check with it.
I mean, I doubt that there will be something at that time here. So most likely this will be up.
So show up on time in case this room is occupied. We'll just translate ourselves among.
That's right. Also space translation. So it will be great. We'll be using almost everything. Oh boy. Okay. Yeah, it's really funny that. Well, yeah, I didn't know about that. Okay. So in lecture 1, we did many things. But one of them was to study what happens on the transformations of this form. Okay? And we defined the notion of a primary field and said that it was a field that transforms as follows. Okay, so this is a field with conformal weights. H bar, okay? If you remember, we also wrote the variation of the field. And I said that it was going to be very important, hopefully yesterday, but it wasn't important yesterday. So it will be important today. So that's why I'm writing it again. Okay, and we discussed many, many things, but also we discussed the behavior of the two-point function. Here I'm going to assume that we have the two-point function of two fields. Both of them have the same, they are the same field with the same conformal dimension. So this was a some normalization factor divided by Z12, 2 times H, and Z12 bar, 2 times H bar. Okay? Very good. Then we move on and said that we're going to consider radial quantization. And the reason was that we wanted to regulate infrared divergences. And we said the way to do it was going to be to identify this spatial coordinate so that we're really working on a cylinder. Time runs this way, space runs this way. We also introduce a conformal map of the form given by this. And then under this conformal map, we send the cylinder to a plane. And surfaces of constant time became surfaces of constant radius. Okay. And sigma 0 equals to minus infinity, the infinite path, was mapped to 0, to the origin, and sigma 0 infinity was mapped to the point at infinity in the plane. Okay? We also realized that part of the map send the dilatation operator So usually people talk about the cylinder on the plane. So you just, if you say plane, you should remember that we're always talking about this. And if we say cylinder, we go back to this. So it's just a terminology. So the dilatation operator on the plane is identified with the Hamiltonian on the cylinder. Okay? Now what we should do today is to take the plane more seriously and ask what are the kind of operations we can do on the plane? What kind of operators we can look there? Okay. So let's consider the plane more seriously and say, imagine that we insert an operator here. Okay. So I'm going to call it phi. I'm not going to worry about the antiholomorphic dependence. It could have, maybe it doesn't have. Now I'm going to have another operator here. Let me call this point z prime. Okay. Now, of course, I can consider the product of these two operators. But there is also something interesting that I can do on the plane, which is say, well, what could happen if I take this operator, I fix this, and I take this operator and move it around in a circle surrounding the operator at the position W. So what I'm going to do is to consider some sort of monodromy. So I'm going to consider the integral along this contour of this operator going around the other operator. Okay? So that looks like a very natural thing that one can try on the plane. Okay? And we would like to know what could this possibly mean. Okay? It looks like a very simple object, but it turns out to be one of the most fundamental operations that we can do here. So it's a good idea to understand carefully what it means. Now, in order to understand carefully what it means, we have to go back to quantum field theory in general. Okay, so here we're talking about general quantum field theories. And when we talk about some operator, right, or some operator identity, after all, when I write this equal to something, it's going to be an operator identity, right? So operator identities in quantum field theory, they only make sense, or they are only defined as long as I tell you, so if I have a statement that some operator is equal to some other object, so let me call it operator 1 is equal to operator 2, this is an operator equation. So this operation, or this equation only makes sense if so happens that the operator 1, the vacuum expectation value with any kind of insertions here, agrees with that of this other guy, okay? So that's the meaning of an operator equation. It's something that is valid for any insertions in correlation functions, okay? Now, yesterday I asked you if you were familiar with path integrals a little bit, and the reason is that if you have some set of operators, say O1, O2, to On, the way you calculate this with a path integral is that you integrate over the space of field configurations, so we can give it a name to the fields in your theory. We don't know what theory we're dealing with. In fact, the great thing about conformal field theories is that we shouldn't even have to write down a Lagrangian to define the theories we're studying. But let's pretend that we knew it, and let's call the field X. So this is something that lives on our cylinder, say. And we have an action that is a functional of that. And we have the operators inserted here. Okay? Now, the only thing that we need about path integrals is that when you do this, the path integral does something very, very smart. The path integral naturally times order these operators. Okay? So this expression is actually time order. Okay? So this is the time order operator. And it does what you think it does, right? So no matter how I put these fields inside here, right? This object, in the Hamiltonian formulation of this, in the standard canonical quantization, it would order these fields accordingly to their time component, where they were inserted, okay? So we will start with the one that was inserted at the earliest time, going all the way to the one that was inserted at the latest time, okay? So every time you see a correlation function, that's actually what we mean, because that's something that is naturally done by the path integral. Now we can go back and keep translating. So if you have time ordering on your cylinder, what would that correspond to on the plane? So we're still translating. So this will correspond to what?
This radial distance.
That's right. All right. So having done that, we see that if we want to think about this operator and discover what it is, we have to insert it in some correlation function. With any operators here. But now we have a problem, right? This object will rearrange this with a radial ordering, okay? So if we look at the radius of the point W, okay, this is a circle, and it's clear that the other field is going around and doing crazy things. So it's not at a particular ordering with respect to this guy. So how can we fix that? Or what is this object doing for us? Well, clearly this object is doing the following. Every time we are on this part, along the integration contour, the path integral is putting the field phi at W first and this one later. And every time we're on this contour, the path integral is doing the opposite. So it makes sense to think about splitting the contour into two contours. One of them would be this one, and the other one would be this one. So this is a trick, but it's a useful trick. Okay. So let me denote these contours as C1 and C2. So we can split this object on the original contour C as an integral over C2. And then on C2, we're going to have phi W, phi of Z prime. Right? That would be the correct order. Plus the integral dz prime on Z1. Now we're going to have phi of Z prime, phi of W. So that's what the path integral will be doing for us, right? Now let me do the following. I'm going to consider not C1, but I'm going to shift it and consider minus C1, okay? So I'm going to reverse the orientation. So when I reverse the orientation, I pay the price of a minus sign, of course. This is a contour integral. So I'm going to reverse the orientation, and this thing will become minus the integral dz prime on this contour, okay? But here there is something interesting. Again, any statement that we want to make about this object will not make any sense unless we take the limit when these contours actually become infinitesimal. The reason is that if we make any statement about this and you insert an operator somewhere here, our statement will be false. Right? Do you see that? The fact that we are dealing with an operator statement means that we have to make sure that whatever statement we make is true for any operators that we insert here. Okay? So we have to take the limit when these two contours actually become the same contour. Okay? So we're going to take the limit, in order to define this, we're going to take the limit when C2 goes to minus C1. That's why I reverse the sign, because we want the two contours to actually become the same. And not only that, we want to take this radius to 0. Okay? So when we do that, what do we find? Well, we find this integral on Z2. And you see that we found something interesting here. We found a commutator. Okay? And that's going to be the connection between the standard quantization conditions that we know and the radial quantization. In other words, this thing here is what we're going to identify as the equal time commutator of operators. Well, why equal time commutator? Because in this limit, you see what's happening, right? The two contours are squeezing each other, and they're actually being localized on the same radius, and that will be the same time. And this object here, again, we don't have to write it, but if we want to, just so that we remember, this object becomes the integral of the radial ordering of the product of these two operators. Okay? And here the contour is Z prime minus W equals to epsilon in the limit when epsilon goes to 0. Okay. So I presume that everybody who is coming tomorrow is here already, so I can erase this. All right. So let's keep our result over there. And let's completely switch gears and discuss something else. We're going to discuss now the stress energy tensor. Of course, you have done it many times already, at least twice, but it doesn't hurt to do it one more time. So in a general quantum field theory that has Poincaré invariance, so T mu nu is a symmetric tensor that satisfies this condition. Okay? So this condition is actually a conservation condition. Okay? It's a conservation condition of what? Do you remember? Well, you would say, well, to have something that is conserved, we usually start with a current. So how come that this looks like a tensor? Well, the reason is that this index over here is the index that tells you what kind of symmetry you're considering. Right? Because we have 4 different kinds of symmetry in 4 dimensions, right? In 2 dimensions, we only have 2. The symmetries that we're considering here are space-time translations, right? So in d dimensions, we have d indices corresponding to the d possible symmetries. For each one of them, we have a current. And the current has a conservation law. Okay? So that's what we have. Now, under a transformation of this form, I didn't write it yesterday, but you did that many times, probably in homework assignments too. This is a conformal transformation if the following is satisfied. Again, we're working in general dimensions. Okay? And the current for conformal transformations, if we concentrate on this, is related to the stress energy tensor in this form. Okay? So this is something that you guys did. All right. But the transformation that is of interest at this moment is the dilatation. Maybe let me just check. So do you know what happens in a conformal field theory? What's the special property of the stress energy tensor? It's traceless. Excellent. So we could save 5 minutes by simply saying that it's traceless. Or maybe just say, well, if we have a dilatation, this implies is that the current for the dilatation is this, right? And conservation of that current, meaning this, implies is that or that the trace is equal to 0. So just the dilatation implies is that the energy momentum tensor or the stress energy tensor is traceless. Okay? So that's all what we need in general from general dimensions. So I should have asked the question even before starting all this. Then we really could have saved 5 minutes. Now we can go back to 2 dimensions. Okay? So again, as we did yesterday, most of our job is going to be translate from general coordinates to our special z and z bar coordinates. Okay? So we start with z, and as I promised, I wasn't going to be consistent with the coordinates that I'm using for the space, for the regular part, or for the cylinder, for what it's worth. Okay, so here I'm using x0 and x1. This is z bar. And what we want to do is to translate or to compute the components of the energy momentum tensor in these coordinates. Okay, so how many components we have to compute? Well, we have to compute the zz, zz bar, z bar z, and z bar components, okay? So which one do I want to compute? I have to decide because the other ones will be exercise for you. I think we can do this one, okay? I mean, it's probably actually it's the simplest. But they are all very easy, right? I mean, we want to compute this, and then all we have to do is to do this calculation, right? Okay. So we just have to put here the 0, 0 part, 0, 1, 1, 0, and the 1, 1, and then compute each of the coefficients, right? So, well, if we do that, then what's going to give us the 0, 0? Well, it's going to be 0, 0. So we look here. Of course, we have to invert the coordinate transformation. So we have x0 is a half z plus z bar, and x1 is 1 over 2i z minus z bar. So the 0, 0 component uses this guy twice, and we get a quarter, right? The 0, 1 component, 0, 1 uses this guy once and this guy another time. So it's with z bar, so we get minus 1 over 2i, 1 over 4i. This guy will give 1, but now with a plus sign because it's a different guy here. And this one will give a quarter again, okay? But the tensor is symmetric. So this is equal to 1, 0. So this cancels out, and the quarter comes out. And this thing becomes 1/4 of t0, 0 plus t1, 1. Okay? And if you're working, so we're working with Euclidean metric. Therefore, it's very easy to see that this guy is nothing but the trace. So we get 0. If you assume that we're working with a conformal field theory, that component vanishes. So in a CFT, we get this thing is proportional to the trace, and therefore we get that this is equal to 0. Likewise, doing the same calculation for this other component, we get 0. And we discover that life simplifies, and we only have to study two components. Okay?
So you just need one of the sum to 0.
No, these two are independent components. Okay? Now, it's really a pity that they depend on z and z bar, right? Wouldn't it be nice if this one only depended on z and this one depended on z bar? Well, sometimes just beautiful things that could happen actually end up happening. So I imagine that people who did this were very happy when they found it. But now we can look at the conservation and see what conditions imposes on these two components, which are the only ones we have to consider. So in order to study the conservation, we have to remember what the metric was, right? So we know that the metric, yesterday, one of you guys reminded us that the metric was this. And of course, the inverse metric would be this. And the reason we need it is that the conservation law, written in this form, is this. That's using the standard Minkowski metric, but of course, we can use any metric we want. In particular, we can go to this metric and study the conservation law of the z component. Let's start with that. So this is supposed to be 0. Okay? Now we want to calculate this object. All the indices here, alpha and mu, take values in z and z bar, right? So we are now using the coordinates z and z bar. So when we do this, what do we get? Well, the first thing is that we discover that if we put here a z bar, we get 0. So the only thing that can be non-zero is when mu is equal to z. So mu has to be equal to z, but if mu is equal to z, alpha has to be equal to z bar, because this has zeros in the diagonal. So this thing is proportional to the derivative with respect to z bar of t zz. And this thing has to be 0. What does that mean? Well, it means that our wish came true. And we can actually cross this from here and make it as beautiful as possible. So tzz is only a function of z. Likewise, you can show that by studying the other component with mu equals to z bar, we're going to get the equation that the holomorphic derivative of z bar is equal to 0, and therefore this other guy is only a function of z bar. All right. Now, remembering that we only have two non-zero components, people like to save a little bit of notation, to save writing by defining some smart notation. So the standard definition that you will see everywhere in textbooks is that you define a holomorphic object T as Z, and by this we mean this component, and T bar to be this object. Okay? So from now on, we're going to be studying T and T bar. Those will be the main objects that we want to consider. Okay.
Sorry, I was studying now on the classical fields. I mean, all these equations on the classical field.
Which equations are only in the classical theory?
I mean these conclusions that t z is a function of only z.
No, this is actually true in the quantum theory too. So let's continue, and you're going to see. Okay. Well, if the conformal symmetry is true at the quantum level, okay. Of course, you could have theories where the theory is anomalous, where some symmetry, some classical symmetry becomes anomalous. So any conclusion that you have will also be false due to the quantum anomaly. Okay. Okay. Having defined this, we again have to make a general detour and go to some general quantum field theory. Okay. And what we're going to discuss now, or what we're going to review, is the following. So for every conserved current, J mu, so conserved, again, means that this is true. We can define a conserved charge called Q, and this is defined as the integral over the space part. So for a fixed time, we compute the integral over all of the space of the 0th component of the current. Now, is this statement quite correct? Is this always true? That you can always define, for every current, you can always define a conserved charge? Well, in most of the examples that we know, or that you guys have studied, it's actually true. In some cases, it's not true. And the reason is that sometimes this integral doesn't converge. So if the integral doesn't converge, then the charge doesn't exist. Okay? So it's not necessarily true that this is correct, but in most cases it's correct. So I'm just going to take it as correct. But remember that sometimes you can only deal with the currents. Okay? So the currents are always there. For every symmetry, there is a conserved current. But it's not true that there will always be a conserved charge, because this integral might not converge. Okay. So why is it conserved? Well, the reason is that when we take the time derivative, of this, and by using this, we convert it into an integral into this space part of the divergence and integrate it over space. Okay? So this integral ends up being, by Stokes' theorem, an integral over. So now this is an integral over the space part, the boundary of the space. Okay? And we always assume that this thing goes to 0 because the boundary of a space is at infinity. When x goes to infinity, this goes to 0. Okay? But is there any other way that this can vanish? Well, it could also vanish if the space didn't have any boundary. Okay? And guess what? That's the case that we have, right? On the cylinder, our space doesn't have any boundary. Okay. You would say, now what? Maybe I should keep on that blackboard the general statements about QFT. So the last statement that we need about general QFT is that every time you have a conserved charge as an operator, you can then use it as a generator of the symmetry. So if you have any operator, say O, the action of your symmetry on the operator O is nothing but the commutator of the conserved charge and the operator. Okay? So why did we do all that? Well, because we want to study the generators of two-dimensional conformal transformations. So who could be the generator? Well, the generators will have to be conserved charges made out of the only two components we have of our friend here, T and T bar. Okay? So our conserved charge is going to be a contour integral. Now we're working on the plane, so we're working at some fixed time and integrating over space. And an exciting exercise is to show that this is indeed conserved. Okay? In other words, that we chose precisely the correct components to write in this expression. Okay. So now we're ready to put everything together. Right? So I've been listing random facts so far. Okay. And I haven't told you why we have been discussing everything that we have. But now we're going to put it together. Let's see, where do we put it together? Well, it could be here. Okay, So what do we want? We want to consider, given a primary operator phi, we now want to consider as a quantum operator the variation under a general conformal transformation. Okay? Now we use the fact that this is supposed to be generated by our charge, if we were correct, by the identification of the charge. Okay? So again, the dots mean the bar of everything that I wrote before. Well, not always, but it does in this case. Okay?
So, the notation of T and T bar, does it
Yes.
imply that T bar is somehow the conjugate T?
No, remember that for us, we have also complexify space, and these two are completely independent operators, right? So Z and Z bar are independent variables. Okay? At some point, we will have to go back, and that will happen, that point will be tomorrow, when we discuss operators and the adjoint of a state. We will have to restrict ourselves to the real slice, and then we will have to impose the conditions of reality. But for the time being, we are fine. Okay. So the next step is to use what we have over here. And what we learned about equal time commutators. Remember, we started the lecture by doing something natural on the plane, and we realized that that natural operation ended up being what we would identify with an equal time commutator of operators. Now we have an equal time commutator of operators, and we can go back and use that this thing is nothing but the integral over this contour of the radial ordering of the product of the two operators. Okay? That means that we can put this, we can write a formula for this operator as follows. Maybe we should have a notation. This should be so using Blackboard 6. Okay, from 1, we ended with that when we're going to write down this formula using the result from Blackboard 6 on 1. We get this is nothing but this object, okay, plus the Z bar part. And the contour is a contour of this form, and here okay, this is very nice, but we also know what this guy is supposed to be. If it's a primary, right, by the results on Blackboard 2, meaning here, we know what this thing is supposed to be. So by 2, this is supposed to be the following. And here, I'm not going to write this part. I'm only going to write this part. So this thing here better be h plus okay, plus the bar part, okay?
So the formula here on blackboard 2, is it true only for primaries?
Yes. It came from here. This was the definition we gave for a primary operator. Infinitesimally, we get this. This was an exercise you all did yesterday, right?
Yeah.
Excellent, yes, of course. All right. Okay, you would say, well, so what? This thing has to be equal to this. Well, can I rewrite this as a contour integral too? Or what is this supposed to do in order to give this answer, okay? So this is a condition I'm imposing on this, okay? So I'm trying to learn something about this radial ordering of the product of these two operators by imposing that this equation be consistent with this equation. That's what I'm doing, okay? So in order to do that, I should write this in a way that looks more like a contour integral. Well, in order to do that, there is a simple way of doing it. I will get exactly this formula if I had started with something like this. So there is a derivative here. So in order to get that derivative, I better start with a double pole so that when I integrate by parts to compute this residue, I produce a derivative. And this will have the epsilon in the end. Okay? So you see what's happening. This is a double pole. So to compute this integral, I have to take the derivative of this guy and evaluate it at z equals to w. And that's what we're going to get here. Okay? Plus, this part is actually simpler because we just have to get this guy evaluated at w. So we can just copy what we have. And here we can have anything that is regular. This will not affect at all the integration along this contour. So we can have anything that is regular, and this formula will give rise to this. Now, putting these two things together, so asking this to be consistent with this means the formula we want means that this object, near the point when z is close to w, or vice versa, this should have an expansion of the form plus regular terms. Okay? Well, you have seen this many times, right? But in the version in higher dimensions, when you were studying OPEs. So this is the operator product expansion of a primary field with the stress energy tensor. Of course, there is also a version for the bar, which I should write at least once. Do you notice any difference between this and this? Did I forget anything? Yeah, the R, right? Good eye, yes. I forgot the R, but I did it on purpose. And the reason is that nobody writes the R. But they always mean it, okay? Just like we never write the time ordering operator, we also think that there is an R here and here, okay? So these OPEs can also be taken as a definition of a primary operator. Okay? Now let's finish this part of the discussion by making the observation that secondary operators, or any other operator, okay? Secondary operators have higher order poles in their OPE expansion with the stress energy tensor. Do you know any secondary operator? Yeah, exactly. Just take a derivative with respect to W of a primary, and you got a triple pole. Okay? Very good. But hopefully soon, we're going to discover that we have been working with another operator, which is not primary. Okay. Let's see. So this one is supposed to be Blackboard 4, right? This one is 3. I think we can get rid of this one. So where are we going with all this, you may ask? Right? This would be a good point to tell you. So the phases of desperation and at this time of the day, after so many lectures. So where are we going? Well, we want to find the quantum algebra of conformal transformations. Yesterday, we found the classical algebra. You remember the algebra we found with the Ln generators? So we want to find the quantum algebra. The reason we want to find the quantum algebra is that then having an infinite dimensional algebra might mean that the symmetries are powerful enough so that if we look at the representation theory of that algebra, that by itself would allow us to solve or to find models that can be completely solved. By solving the model means computing all correlation functions exactly. Okay? So that's where we're going. We have to find the quantum version of the algebra we found yesterday, okay, for a general conformal field theory in 2 dimensions. Then impose conditions on the Hilbert space that we want to construct. The Hilbert space will have to be given by representations of that algebra, and hopefully that will give us enough information in particular cases to completely solve the theory. Okay, that's where we're going. That we're going to get there, well, that's a different question. But that's where we're going. So we've been discussing the stress energy tensor and how it generates the conformal transformations. But now it's only fair to consider the conformal transformations of T itself. Okay? Well, in order to do that, what we have to do is to compute the OP of the energy of the stress energy tensor with itself, right? But in order to do it, let's actually go back a little bit and use this formula, okay, to learn something about T. So let's rewrite this formula quickly here. In fact, I'm only going to write this part. This is all we need. The reason is that if you look at this thing here, wow, I cannot believe it. So again, by looking at Blackboard 2, this thing is nothing but the correlation function or the 2-point function of two fields. Let me call them phi and phi of z and phi of w, evaluated at w, each of conformal weights given by what? If you look at that formula, if I want to get, forget about the h. The h is irrelevant. Yeah, 1,0. Exactly. So if both these fields are of conformal weight 1,0, then their 2-point function will exactly give me this, right? But now look at this. So on this side, I have the field phi, and I have the field phi here. So just from here, I can conclude that T has to be an operator of conformal weight, well, 2,0. Okay. So T has conformal weight 2,0. Now, do we know that T is a primary field? We don't know, okay? But just the fact that it has conformal weight 2,0 tells us that if we compute its OPE with T of Z, meaning we're applying this conformal transformation to this guy, then it has to have a piece that looks like 2 times Z minus W squared times T of W and the simple pole, okay, plus regular terms. But nobody has told us that this field has to be, what is that happening? Sorry, I hope it's not too hot in here. Okay. But we don't know if this field is a primary operator, okay? So we should allow for higher order poles. How high can they be? What do you think? Well, roughly speaking, we know that each of them can produce something that is quadratic. So at most, it can be something of a pole of order 4. Can I also have a pole of order 3? What do you think? Could I have a term? Well, I said that the maximal order can be of order 4. But can I have something of order 3? No, why not? Exactly. This is supposed to be a bosonic field. So I cannot pick up a minus sign. And therefore, the cubic part is not allowed. So the only thing that I can possibly have in addition to this is a pole of order 4. And moreover, I cannot have any operator here. I ran out of operators already. So this thing has to be a constant. And people like to call this constant C over 2. The 2 is just normalization. There is nothing fundamental about the 2. Okay. So C could be 0. If C is 0, then the stress energy tensor is a primary field. If it's not 0, then it's not. Okay? So this is our first non-derivative example of a field that is not a primary field. So much of the goal is to classify theories by their values of C. So C is a number that depends on the theory. Okay? So this is the first time we see something that depends on the theory we're talking about. Everything else has been general. So let's consider what happens under infinitesimal transformations. Okay. In other words, we want to see what happens to this object. Now we can again go back and use the same trick, but now in reverse, right? So we want to find this knowing the OPE. Okay, so now we're going backwards. So we went from here and guessing this, or deriving this. No, we didn't guess, we derived this. And now we want to start from here and get this, allowing for this term. Okay, so the first two are trivial. The first two are just the standard terms. So I'm going to write them, and while I write them, I'll give you a chance to figure out what the third one has to be. Okay? Let's see if you can get it before I finish writing the first two. So the first two, I mean, I'm even writing them in the wrong order. There is no such a thing as a wrong order, but it's not natural. Okay. So did you get it already? I'm trying to keep you awake. So the last term is the term that we come from this. Okay? Well, in that term we have to integrate by parts 3 times, right? And therefore we get a factor of 6, which with a factor of 2 that we have there becomes a 12. And we get the third derivative of the parameter or the function epsilon. Okay. If you have some spare time, as an exercise, you can compute the finite form of this transformation, which is something of the form when z goes to f of z, t goes to this, as it should, because it has conformal weight 2, 0, okay? But it has an extra term, and that's why it's not a primary field. If this was a whole story, it would be a primary field, but it has an extra piece, which depends on C, and it's a little bit complicated. Okay. And this complicated thing has a name. It's called the Schwarzian derivative, thought of as an operator acting on the function f. But now, in the previous CFT courses, you learned that the stress energy tensor was a special kind of field. It wasn't completely random, right? Was it Was it really something random or was it quasi-primary? I mean, I guess you learned that the stress energy tensor was a quasi-primary field. So how can it be that it's quasi-primary and it has this funny transformation law? What could be the resolution? Remember that the difference between quasi-primary and primary is that one is more awesome than the other.
Local and global transformation.
Sorry, what's the difference?
Local transformation?
Local or global transformations, right? So, what do you think has to happen to this nicely looking object when F happens to be a global conformal transformation? Is 0, indeed. So that's, if you're Schwartz, you could guess, you could find this object by looking for the unique object with the correct conformal weight that vanishes under this transformation.
TZ transforms into T with an argument F of Z.
Sorry?
I mean, on the right hand side, if you have T, okay, on the right hand side, it should have argument probably T of F of Z, not T of Z, T from Z.
Yes, sorry. Very good. This is exactly. Yeah, that's correct. Yeah, thanks. Okay, so you could also try that out. You could forget about this and try to find the most general object that transforms, that vanishes whenever the transformation is a global transformation. So T is a global primary, or an SL to C primary. Okay. All right. So as I said, the goal of today's lecture is to get to the algebra, to the quantum algebra. So in order to get to the quantum algebra, again, we have to do the same thing that we did yesterday. Yesterday, what we did was to expand this function in a Lorentz expansion, right? Here, what we have to do is to expand T in a Lorentz expansion again to find individual generators. So this is called the mode expansion of T. So again, we assume that T will have a Lorentz expansion at this point, the 2 looks weird, but we're going to see that it's convenient to define it this way. But there is nothing deep about putting the 2 here, okay? Or the minus sign, for what it's worth. Okay. But we're going to see that it's convenient. So this is in hindsight, this is the best choice. So inverting this, we can write ln as the integral of z to the n plus 1 times t of z. So do you remember what my convention is for integrals? They all have a 1 over 2 pi I everywhere, right? So you see it works perfectly. So the last thing we want to do today, and therefore we can use the standard trick, is to compute the algebra satisfied by these operators. Okay, so step 1. Of 98. Let's compute the commutator of ln with t at w. Okay? The reason is that this is something that we have done already, basically. Well, ln is given here. So what we have is integral over z of okay. So here I'm using this formula for ln. Okay. So we're using the very first thing we derived in the lecture today. Now, we use this. And we bring it here and hope that it stays. And we use it. And what do we get? Well, we have to perform these integrals. So we have c half over z minus w to the 4th plus 2 times minus w squared dw plus 1 over all this plus regular, all this multiplied by z to the n plus 1. Okay? Now, the regular pieces will not be important for us, right? Because the contour will kill them. And then what we have to do is just to compute all these integrals. This integral with this integral with that. The t's only depend on w. So all these calculations are trivial. So you can either put them in Mathematica or you can do them by hand, as I did. So the first one is the integral dz z to the n plus 1 over z minus w to the 4th. And this is nothing but 6 of, so you can see that you have to take 3 derivatives. So the first derivative brings an n plus 1, the second an n, and the third an n minus 1. Okay. And the last thing is evaluated, the last power of this guy is evaluated at z equals to w. So we get w to the n minus 2. Okay, that's the first one. The second one is the zn plus 1 over z minus w squared. And this thing is n plus 1. Okay, just single derivative, w to the n. And the last one is the integral dz zn plus 1 over z minus w, and this is just wn plus 1. Okay? So having done that, we find that this is nothing but c over 12. The first term, the 2 with the 6 is a 12, and we have n times n squared minus 1, just simplifying a little bit, times w to the n minus 2 plus 2 times n plus 1 w to the n t so that's the full answer. Okay, so what's the last step? Well, we wanted to compute this, right? So if we define Lm as an integral dw, w to the m plus 1 of t of w, all we have to do is to integrate that against this. Okay? So our ln m will be the integral dw w to the m plus 1 of that object we found there. Okay. The first term is something interesting, right? So you look at this with this guy. There is no dependence on anywhere else on w except for these two factors. And therefore, this integral vanishes unless we get exactly 1 over w. But we get 1 over w only when m plus n is equal to 0. So the first term is this times a canonical delta of this form. That's the only time we're going to get something non-zero from here, because there is no other dependence. Now the next term will give us 2 times m plus 1, right, coming from there. And now we have a t of w, w to the n, which combined with this guy that we have here, precisely matches the definition of L m plus n. But this doesn't look like the algebra we had yesterday. So it better be that the third term fixes things nicely. Okay. Now the third term, we have a derivative. So we have to integrate by parts. Okay. So integrating by parts, so let me just write here what we have to do. Okay, so integrating by parts, this then becomes very nicely something proportional to the same operator, and combining these two guys, we finally get our result. And this is called the Virasoro algebra. Okay. Of course, we also have our L-bar version. Okay. And the important thing to notice, well, something that we can notice immediately, is that the quantum anomaly, or this quantum part that appear, is going to be something that disappears exactly when we only consider the generators related to the global transformations. So if we only concentrate on the subalgebra generated by L0, L minus 1, and L1, so C has no effect. And the algebra is then the algebra that we discussed, the global algebra. Okay? Very good. So we did it. We found the quantum version of the algebra that we want to study. And using this algebra, trying to construct Hilbert spaces that satisfy physical conditions, we're going to discover that in an infinite case of families, the algebra is powerful enough to fix everything for us. Okay? And those would be what are called minimal models. And that's what we hope to get to. Okay? So I'll see you tomorrow at 9:30, right?